So for today's lesson, what we're going to be talking about is ionic compounds. Now that word ionic should sound a lot like a word that you heard back in grade 9 chemistry, and that's ion. If you remember, an ion is a charged atom, and it becomes charged by gaining or losing electrons. So if we're talking about electrons, we must be talking about the structure of an atom. So if we look back at our Bohr-Rutherford diagrams, here we have a Bohr-Rutherford diagram for potassium and one for chlorine. You can see that potassium has 19 protons and 20 neutrons in the nucleus, and then we have a series of orbits. We have our electrons. We'll recall that we have 2 electrons in our first orbit, which is as many as it can hold, 8 in the second, 8 in the third, and then it's got 1 in the fourth orbit. Chlorine has 2 in the first, 8 in the second, and then it has 7 in the outer orbit. Now, the one thing we want to think about is think about the noble gases and what made them special. Well, a noble gas has a full outer orbit. They have 8 electrons in their outer orbit, and we can see a couple of them in the diagram at the side there. We've got things like neon and argon. The other thing that we know about the noble gases is that they're very unreactive. They don't want to react, and the reason they don't want to react is because they're happy with their electron structure. They don't want to change the way things are. And in fact, you can think of the noble gases as being the cool kids in school that all the other elements want to be like. So chlorine here, potassium, they all want to be like a noble gas in that they want a full outer orbit. So the question is, how are they going to get that full outer orbit? Well, they're going to trade electrons. So if we look at chlorine here, it has 7 in the outer orbit. It has 2 options on how it gets a full outer orbit. It could get rid of all 7 in that outer orbit, and then the next orbit in would be full, or it could get 1 more electron in that outer orbit, giving it 8, and that would be full. So we could get rid of all 7 or get 1 more. And we're going to think that whatever number is lower is the easier route. So getting 1 more is easier than getting rid of 7. With potassium, it has 1 electron in its outer orbit, so it has 2 options as well. It could get 7 more, or it could lose that 1 electron. So you can probably see how this is going to happen. When potassium and chlorine come together, they're going to cut a deal. Potassium says, listen, I would really like to get rid of my 1 electron. Chlorine says, listen, I'd really like to get 1. So what's going to happen? Potassium sends its electron over to chlorine. When that happens, now the next orbit in is full for potassium, so it has a full outer orbit. Chlorine, it has a full outer orbit now because it had 7, gained 1 more, now it has 8. So what has this done to the charges of our atoms? Before, we had 17 protons and 17 electrons. So 17 positive protons, 17 negative electrons, the overall charge was 0, or neutral. The same is true with potassium. 19 positive protons, 19 negative electrons, neutral. But we've changed things. Chlorine has now picked up another negative electron. So it was neutral, and we've added 1 more negative to it, so its overall charge is going to be -1. Potassium, its charge, it was neutral, we've taken away 1 of the negatives. So now there's more positive protons than there are negative electrons. So its charge is going to be +1. Now, what do we know about positives and negatives? We know that they want to be together, that opposites attract. So we have an electrostatic attraction between these 2. They want to be together, and they form what we call an ionic bond. An ionic bond because ions are charged atoms. Okay, let's look at another example. Here we have beryllium, which has 4 protons, 5 neutrons, and 4 electrons. So it has 2 electrons in the outer orbit. Nitrogen here has 7 protons, 7 neutrons, and 7 electrons in its 2 orbits. It has 5 electrons in its outer orbit. Beryllium has 2 in its outer orbit. So, what do these guys want to do? Well, beryllium, having 2 electrons, its choices are lose 2 or gain 6 more. What's easier? Well, we're going to assume again the lower number, so losing 2. Nitrogen, it wants to gain electrons. It has 5, so it could gain 3, or it could lose all 5. Easier to gain the 3. So what's going to happen? They meet up, they start to cut a deal. Beryllium says, hey, here you go, don't want the electron. Nitrogen says, thank you very much. Beryllium sends another one over, And nitrogen's happy about that as well. But nitrogen says, hold on here. I'd like some more electrons. Beryllium doesn't want to give up any more. It's given away its 2. It now has a full outer orbit, remembering that the inner orbit only needs 2 electrons to be full. Nitrogen only has 7, so it needs more. So what happens? Well, beryllium calls up a friend, and we get another beryllium atom. It has, again, 2 electrons in its outer orbit, and it sends 1 over. Now the nitrogen is happy. And so, but beryllium is not happy. It says it showed up, wanted to get rid of its electrons, and now it's only getting rid of 1. So what happens? We get another nitrogen on the scene. 7 protons, 7 neutrons. And again, you can see this is a bit of a pain to go through and have to draw a Bohr-Rutherford diagram every time we need to add a new element. So beryllium sends it over. It is now happy. It's gotten rid of its 2 electrons. Nitrogen, it wants 2 more. So it's not happy. So what do we need? Well, we need another beryllium. And this process looks like it's going to keep going and going, but let's just wait and see. So 5 neutrons, 2 electrons in the first orbit, 2 in the outer. It sends 1 over, and this one sends 1 over as well. And then, now this beryllium's happy, and that nitrogen's happy. And so we've worked everything out. What does this do for us? Well, when beryllium combines with nitrogen, we're going to get a formula like this, where we have beryllium, and we have 1, 2, 3 of them combining with 1, 2 nitrogens. And that's how we get the formula Be3N2. Now, that was a lot of work. Is there a faster and easier way to do this? Also, note, what are the most important electrons here? Well, really, these ones on the inside didn't really matter for me too much. I didn't need to worry about them. I was only concerned with these outer electrons. Now, we give these outer electrons a name. We call them valence electrons. Now, valence electrons are the ones in the outer orbit, and they're going to control what the charge of the atom is, because if you have 2 electrons, you're going to want to get rid of those 2, and you become +2. If you had 5, you'd want to gain 3 more, you get a full outer orbit, and it's going to be -3. So the valence electrons determine what the charge is, and that's actually going to control how they combine. So they're the most important ones. It'd be really nice if I could figure out a way where I could figure out how many valence electrons I have without going through and drawing a full Bohr-Rutherford diagram. And in fact, there is a way. Okay, let's take a look at some of the elements we've been talking about on the periodic table. Potassium is over in the very first column. It is in group Ia. Now, we don't worry about the A. The I is a Roman numeral. I is the Roman numeral for 1. Potassium had 1 valence electron, and it's in group 1. Interesting. Then let's take a look at beryllium. Beryllium is in group Ia, or group 2. Beryllium had how many valence electrons? It had 2. So 2 valence electrons in group 2. Interesting. Let's go over to nitrogen. Nitrogen is in group Va, or group 5. So it had 5 valence electrons, and it's in group 5. Chlorine, it had 7 valence electrons. Which group do you think it's in? Well, it's in VII, and if you don't know your Roman numerals, that's 7. So 7 valence electrons in group 7. So essentially, we can use the information on the periodic table as to which column it's in to determine the number of valence electrons. That's going to make my life a lot easier, so I don't have to go through and draw a full Bohr-Rutherford diagram every time I have to do this to figure out the number of valence electrons. Now we're going to introduce you to a new type of diagram called the Lewis dot diagram. And it's going to focus on showing the more important information, where it's not going to show us all of the electrons and where they're positioned, just the valence electrons. So let's go through and do one for potassium. The symbol for potassium is K. And now we're going to look on the periodic table and say, okay, potassium is in group 1, therefore it has 1 valence electron. And to show that, we're going to put 1 dot. So the number of dots is going to represent the number of valence electrons. For chlorine, Chlorine is Cl. It is in group VII, or group 7, so it's going to have 7 valence electrons. So I am going to put 7 dots. So each dot again representing a valence electron. Now, rather than doing what we did before, I can see how potassium is going to send 1 over to chlorine, and we're going to get our compound of potassium chloride. That's a lot easier than going through and drawing those Bohr-Rutherford diagrams. Let's do it again for beryllium. Beryllium, Be, it's in group 2, so it has 2 valence electrons. I'm going to put them right there. With nitrogen, nitrogen, again, is in group 5, so it's going to have 5 valence electrons, because V is 5. So 1, 2, 3, 4, 5. And again, this would make the whole process of drawing out how that compound forms a lot easier. I can also use this to figure out what the ionic charge of each element is going to be. I'll look and say beryllium. It has 2 valence electrons, so what does it want to do to get a full outer orbit of 8? Well, if you have 2, you could either lose 2 or gain 6. Which is easier? Again, we're going to go with the lower number, so losing 2. So which charge is going to be B plus 2? Nitrogen, what does it want to do? Well, it has 5, so its 2 options are lose all 5 or gain 3 to get it to 8. So it's always losing all of them or gaining whatever it needs to get to 8. And then you look and say which one is the lowest number. That's what it wants to do. So in this case, it wants to gain 3. So we're going to get nitrogen 1, 2, 3, 4, 5, 6, 7, 8. What's its charge? It is now -3. So we can draw the Lewis dot diagram very easily, and we can also draw the Lewis dot diagram of the ion. You'll notice here that I didn't put any dots around the beryllium ion because we're trying to show the original valence orbit. And now that orbit, because it's lost those 2, does not have any, and that's why there are no dots.